Welcome to DA classes. Today we're going to learn about relative velocity. This concept is fundamental in physics and helps us understand how objects move relative to each other. Before we dive into relative velocity, we need to understand what a frame of reference is. A frame of reference is simply a perspective from which observations are made. For example, when you're sitting in a moving train, the person sitting next to you appears stationary from your perspective, but to someone standing outside, both of you are moving. Now, let's define relative velocity. Relative velocity is the velocity of an object as observed from a particular frame of reference. Mathematically, if VAB represents the velocity of object A relative to object B, then VAB equals VA minus VB. Let's look at a simple example. Imagine a car moving at 30 meters per second eastward, and a train moving at 50 meters per second eastward as well. The car's velocity is 30 meters per second eastward. The train's velocity is 50 meters per second eastward. What is the velocity of the car relative to the train? To find the velocity of the car relative to the train, we use our formula. V car train equals V car minus V train. Substituting our values, we get 30 meters per second minus 50 meters per second, which equals negative 20 meters per second. The negative sign indicates that, relative to the train, the car is moving westward at 20 meters per second. From the perspective of someone on the train, the car appears to be moving backwards at 20 meters per second. Let's look at another example, this time in 2 dimensions. A boat is crossing a river. The boat can move at 4 meters per second in still water, and it's pointed directly across the river. The river is flowing at 3 meters per second downstream. What is the actual velocity of the boat relative to the shore? This is a perfect example of vector addition. The boat's actual velocity relative to the shore is the vector sum of the boat's velocity relative to the water and the water's velocity relative to the shore. We can represent this graphically with vectors. Using the Pythagorean theorem, the magnitude of the resultant velocity is square root of 4 squared plus 3 squared, which equals 5 meters per second, and the direction is at an angle theta, where theta equals the inverse tangent of 3 over 4, which is approximately 37 degrees downstream from the perpendicular. Understanding relative velocity has many practical applications. For pilots, it helps in calculating the actual ground speed and direction when flying in windy conditions. In navigation, it's essential for determining the correct course to reach a destination when crossing currents. Even in astronomy, relative velocity is crucial for understanding how celestial bodies move with respect to each other. To summarize what we've learned, relative velocity is the velocity of an object as observed from a particular frame of reference. Mathematically, it's represented as VAB equals VA minus VB. In 2 dimensions, we use vector addition to find the resultant velocity. Understanding relative velocity helps us solve many real-world problems involving moving objects. Thank you for watching. Please like and subscribe to the video